BC Calc, this is your day 73 notes. Today we're going to be talking about a pretty awesome topic. You're going to love it. It's logarithmic differentiation. So I'm going to jump essentially to that part of the lesson because there's a lot of review to get started that I think we'd benefit from doing in class tomorrow. Maybe I'll have you pair up and work on some of these integrals with one another. So we're going to write the general properties at the top. And if you want to start getting a head start on this, I'll leave that up to you. But you've got four integrals here, two indefinite, two definite at the bottom. And then on the next page, we'll also do these three in class where you're going to practice finding some derivatives. So we'll take some time in class to go over those. But at the very bottom, we have what are those log properties again. So we're going to recap the log properties and then actually, as promised, prove property number one, that the product property does work. And these rules do help us to find derivatives in this process known as logarithmic differentiation. So as a reminder, we have the following. The product property here is ln A plus ln B. Multiplication expands to addition, division, we know expands to subtraction. And for power property, we can bring the power out front. And like I was just mentioning, these will help, these properties, I promise, in finding dy dx really for some more complicated looking examples. It's going to greatly help us to use that rule. Okay. So to prove property number one for you, like it says at the bottom of your page, I'm going to let y1 equal ln of a times x. And we know that a product expands to addition. And I'm going to let y2 equal just ln x. And what I'll show you is that if you find the derivative of each, we know derivative of ln of x is 1 over x. And the derivative here would be 1 over the quantity ax, but because of chain rule times a. Well, even though when I find the derivative here, multiplying by that constant on the inside, notice how 1 over ax times a, the a's would cancel, and you'd still be left with 1 over x. So the derivative of both of those, y1 and y2, come out to be 1 over x. And even though they're different functions, what we know is that if they have the same derivative, all that happens is that they differ by a constant. So moving on from there, we know that y1 ln of the quantity ax would equal y2 ln x plus some constant. So we're going to let x equal 1, and you'll see why we want to let x equal 1. It's going to make our job pretty easy, that if x equals 1, ln of 1 is 0, so that's a good choice to make here. So from there, we get ln of a, because remember x is 1, ln of a equals ln of 1 plus c. And since ln of 1 is 0, we get that c is the value for ln a. So if I come back to this statement here that the ln of ax equals ln x plus some constant, we just prove that constant is ln of a by choosing this specific x value equaling 1 here. So therefore, we can come up with a statement that the ln of ax is equal ln x plus ln a, thus proving that the product property does in fact work. So kind of nice how we can do that neatly using some derivative properties that we know. And what we're going to do right now is apply this in the context of using logarithmic differentiation. So if you turn to the next page in the notes, you'll see the example y equals the natural log of x times x square root of x plus 5 over x minus 1 cubed. If you wanted to find the derivative of this natural log function, what you would really need to consider is, I guess it would be 1 over this mess, right, times the derivative of the inside with chain rule. And oh boy, what do we have for the derivative of the inside? We have product rule, we have quotient rule, we have chain rule. There is so much going on in there. But here's where log properties are going to save the day. So definitely want to consider for this one, use all of your log properties to expand this expression such that when it's expanded out completely, it will be much easier for you to identify and find the derivative. So we get y equals, this would be natural log of x, and then we know this is radical x plus 5 to the 1/2, so multiplication will expand to addition, the 1/2 comes to the front, so 1/2 ln x plus 5. And then division, expansive subtraction, pull the 3 out to the front, so 3 ln of x minus 1. So now that we've written in this as sums and differences here, the derivative of a sum is the sum of the derivatives. So you can find the derivative, of course, of each of these pieces, and in the end be able to figure out the derivative much simpler than if I had tried to use the general rule for natural logs, which is 1 over the quantity times its derivative, which would be pretty complicated here. So therefore, dy dx would equal 1 over x plus, this would be 1/2 times 1 over x plus 5. Derivative of the inside is just 1, so that's fine. And then over here, minus 3 times 1 over x minus 1. Derivative of the inside is still 1 there. So there's not really too much to do to clean this up. I'm not going to make you make common denominators or anything like that, but maybe just each fraction individually, I can multiply those together to get 1 over 2 times x plus 5 minus 3 over x minus 1 for the last fraction. So that looks much, much, much cleaner. And I guess, could we have gone through the process that I described up here earlier of doing 1 over and then multiplying by the derivative of the inside? Sure, but it's going to take you much, much longer, and I think you'll be much happier using some log properties to separate and expand, and then be able to differentiate from there. So looking to number 2, the sad thing about number 2 is that there's no natural log to work with, so I can't use those properties of expanding. And if I said find the derivative here, oh boy, does this look complicated, doesn't it? We've got lots of exponents, products, quotients. On the other side, it's y to the 2/3. Okay. So here's the thing. If there's no natural log already there, why don't we introduce the natural log? This is truly what logarithmic differentiation helps us to do. So logarithmic differentiation. We're going to start in this example by taking the natural log of both sides. When you have a derivative that looks as complicated as this one does, let's take the ln of y to the 2/3 and the ln of x squared plus 1, 3x plus 4 to the 1/2. And then the bottom is the 5th root of the product, 2x minus 3 and x squared minus 4. Okay. Why is that a useful first step? Because now I can expand and then find the derivative of both sides. So when I expand, it's going to look a little bit different because this one just says didn't have ln to start. So when I expand, in this case, the 2/3 is going to come to the front. So 2/3 ln y. I wish I had smaller handwriting. I hope I fit this all in here. So it's going to be ln of x squared plus 1. The multiplication will become addition. Bring the 1/2 out front, plus 1/2 ln 3x plus 4. On the bottom, we're subtracting. We got to pull out the 1/5 and then expand that product there. So it's going to be minus 1/5 ln of 2x minus 3. And then what I'm going to do is the 5th root certainly applies to both of these. I'm going to write minus 1/5 again, distribute that negative 1/5 in to the ln of x squared minus 4. Okay, so we've gotten everything expanded here according to our log properties. Now we can actually take the derivative of both sides. So when I take the derivative of the left side, we have our constant 2/3. The derivative of ln y is 1 over y dy dx. Okay, so a little bit of an implicit differentiation feel on that left side as well. And the derivative of the right side with respect to x is going to be, on this case, 1 over x squared plus 1 times the derivative of the inside, which is 2x. So if you're okay with it, I'll write it as 2x over x squared plus 1. Then it's a plus 1/2 times, it's going to be 1 over 3x plus 4 times 3. So we'll put that 3 on top. Minus 1/5 times 1 over 2x minus 3 times the 2 for the derivative of the inside. And then at the end, minus 1/5. This would be 1 over x squared minus 4 times the derivative, which is 2x. So that's going to go on top. Okay. So we're getting pretty close to having this in terms of dy dx. I guess we can clean up a few more things before we get there. But to get dy dx alone, I'm going to have to multiply both sides by 3/2 and then also by y. So we're going to get dy dx equals 3 halves y, or 3y over 2, times this whole quantity. 2x over x squared plus 1, plus, let's just make that 3 over 2 times 3x plus 4, minus 2 over 5 times 2x minus 3, and then minus 2x over 5 times x squared minus 4. Boy, did we just jump right into it. I didn't even give us an easy example to start. This is fairly complicated. Okay, it's not complicated once you expand, is it? I mean, it's just a lot of derivatives of natural logs along the way. It looks like a complicated answer in the end, but logarithmic differentiation really saved us a lot of heartache in the end of trying to do this, first of all, implicitly, and then also with all of our product, quotient, and chain rules on this side. That's going to take forever. Now, notice that dy dx is still in terms of y. So if needed, we could plug y back in if needed. When would it be needed? It would be needed, I guess, if it were a multiple choice question. It may not be in terms of y. If everything's in terms of x, well, then you just go to your original expression. It would be, I guess, to get y alone, you'd have to take, raise both sides to the reciprocal 3 halves power. It would be this thing to the 3 halves that I would plug in for y, and that would be an expression all in terms of x then. So just know that in the end, when you multiply that y to the other side, you can then replace y with what it is in terms of x and get an expression for dy dx that way as well. So this is a fairly intense question. We'll do another one like it. So go to the next page here. If you're wondering, well, like, how should I know if I want to do like product quotient chain rule versus how should I know if we're going to use logarithmic differentiation? Well, you're going to refer to the AP exam directions. The AP exam will at times direct you to use logarithmic differentiation. Or could we choose it just if the equation looks pretty complicated to find the derivative? Absolutely. So we're going to do that for this next question here. Let's use logarithmic differentiation to find the derivative because, yeah, there's a lot of moving pieces. You have the skills to be able to do this without. But maybe you'll trust me here and think that taking the natural log of both sides is a good start. So it's going to be ln y equals, when I take the natural log of this side, let's just start expanding it right away. So if I take the natural log here, the 1/2 is going to come out in front of the ln of cosine x. And then on the bottom, we're dividing by that product. So I'm going to subtract, pull the 2 out in front of ln x. And dividing by sine x, let's subtract again the ln of sine x. So once you have everything completely expanded after taking the natural log of both sides, now you can take the derivative of both sides. Similar to what we saw in the last case, this is going to be 1 over y dy dx. And then the derivative of ln cos x is 1 over cos x times the derivative there, which is negative sine x. So it's going to be negative sine x over cos x after doing that. Minus 2 times 1 over x. And at the end, minus, you're going to get 1 over sine x times the derivative of sine, which is cos. So it's going to be minus cos over sine. So to get dy dx alone, one quick step of multiplying the y to the other side. Oops. And if I start cleaning things up a little bit, this would be half of negative tan, or negative 1/2 tan x, right? And then this would be minus 2 over x, and minus cos over sine, that would be minus cotangent. So in thinking about why am I making all these replacements, I mean, they're easy replacements to make according to those quotient identities for trig there. But most likely in a multiple choice, you're going to see this in here, okay, instead of sine over cos and cos over sine. And beyond that, it's easy enough just because y was a little bit easier to write. Maybe I'll even replace y in the end and have that the derivative dy dx is the square root of cos x over x squared sine x times that whole business negative 1/2 tan x minus 2 over x minus cotangent x. Okay, so that's as far as I'll take it for now. Maybe there'd be a little bit more simplifying. I don't know if we distributed, but that looks pretty good to me. Okay, so does this method always work? Well, I don't know, should we try it for something that we definitely know the derivative of really quickly? We know for y equals x squared that dy dx is 2x. We know that. Does it work for y equals x squared? Well, ln y would equal ln of x squared. Bring the 2 out front. Okay, and then take the derivative of both sides. So we get 1 over y dy dx equals 2 times 1 over x. So if I multiply both sides by y, I get dy dx equals, multiply this side by y, 2y over x. But what does y really equal? Y is really x squared. So 2x squared over x is 2x. So the answer is yes. I'm excited about that. Yes, it does really work every single time using logarithmic differentiation. Should we choose it for something like y equals x squared? No. So if it's something you can easily apply the power rule to, you're not going to want to use it for something like that. It takes a lot more steps to get there. But just know that it does always work, which is the good news. Definitely want to use it for complicated situations like the one above, or again, if the AP exam directs you to do logarithmic differentiation, that's what we want to do. So that's all the new stuff for today. At this point, when we come back tomorrow, we'll do the other examples of finding some integrals and derivatives with natural logs. And that's it. We'll see you tomorrow.